Imagine gazing up at the vast, inky canvas of the night sky, a breathtaking panorama of glittering stars and distant galaxies. It is a view that humbles us, reminding us of our tiny place within the boundless cosmos. Among the countless mysteries that whisper down from those distant reaches, one question stands out with profound significance for life as we know it. Where did all the water in the universe come from? This isn't just a question about the water in Earth's oceans, but about every drop, every ice crystal, every wisp of vapor found across the vast expanse of space. It is the cosmic water's grand question, one that forces us to look beyond our familiar world and into the very fabric of universal creation. At first glance, the answer might seem straightforward. We encounter water every day. It fills our oceans, carves our landscapes, and courses through our very beings. It seems abundant, ubiquitous, and utterly essential. Yet, to truly grasp its cosmic origins, we must embark on an extraordinary journey, stretching back billions of years to an epoch before stars ignited and galaxies swirled into existence. We are talking about a journey into the primordial universe, a realm vastly different from our current perception, where the building blocks of water were scattered and unformed. The universe, in its earliest infancy, was an incredibly hot and dense environment, a chaotic soup of fundamental particles and pure energy. There were no complex molecules, no intricate structures, and certainly no liquid water. The conditions simply did not permit it. Yet, within that initial furnace lay the seeds of everything that would eventually come to be, including the two most crucial components of water, hydrogen and oxygen. The story of water, therefore, is not just a tale of chemistry, but an epic saga interwoven with the entire history of the cosmos, beginning not with a splash, but with the most basic elements. Consider the sheer scale of this inquiry. We are not just pondering the origins of water on one planet, but its presence everywhere it has been detected, from the icy rings of Saturn to the swirling nebulae where new stars are born, from the atmospheres of gas giants to the ancient, frigid surfaces of distant dwarf planets. This pervasive distribution of water strongly implies a universal mechanism for its creation, a process that transcends individual celestial bodies and speaks to the fundamental physics and chemistry governing the cosmos as a whole. To unravel this grand question, we must first appreciate what water truly is: a molecule composed of two atoms of hydrogen bonded to one atom of oxygen. This seemingly simple chemical formula, H2O, belies a profoundly complex and fascinating origin story. The hydrogen part of the molecule has a relatively ancient lineage. It was forged in the fiery crucible of the Big Bang itself, alongside helium and trace amounts of lithium. These elements were the universe's first actors, the raw, fundamental material from which everything else would eventually be constructed. So, the hydrogen component of water, we can say with a high degree of certainty, has its roots in the absolute beginning of existence. However, oxygen, hydrogen's indispensable partner in the water molecule, has a very different and much later origin story. Oxygen is a heavier element, and its creation demands far more extreme conditions than those present in the universe's infancy. It cannot simply appear from the primordial soup. This immediately tells us that water, as a molecule, could not have existed in the very first moments after the Big Bang. There was simply no oxygen available. This fundamental difference in the birthplaces and timelines of hydrogen and oxygen is the key to unlocking the cosmic mystery of water. It forces us to look beyond the initial cosmic event and into the subsequent processes that shape the universe over billions of years. The very existence of oxygen, and consequently water, is a testament to the universe's ongoing evolution. It is a story not solely of initial conditions, but of cycles of creation and destruction, of stars living and dying in spectacular fashion, gradually enriching the cosmos with the heavier elements necessary for molecular complexity. Without these stellar processes, the universe would remain a much simpler, perhaps barren place, utterly devoid of the very molecules that underpin life. Thus, when we ask, where did all the water in the universe come from? We are asking a two-part question. First, where did the hydrogen originate? The answer is the Big Bang. Second, where did the oxygen originate? The answer is the hearts of stars, particularly the most massive ones. The combination of these two elements, however, is not a simple matter of them existing in the same vicinity. They must interact under specific conditions to form the stable covalent bonds of the water molecule. This requires environments where temperatures are cool enough for molecules to form without being instantly torn apart by intense radiation, yet dense enough for atoms to readily encounter each other. The ultimate origin of water, therefore, is an intricate dance of cosmological and astrophysical processes stretching across the entirety of cosmic history. Our cosmic journey into water's origins now focuses intently on hydrogen, its primary constituent. Hydrogen's ancient birth is intrinsically linked to the very first moments of the universe's existence, a story that began approximately 13.8 billion years ago with the colossal event we call the Big Bang. Understanding hydrogen's primordial genesis is the foundational step in comprehending where all the water in the universe came from. In the immediate aftermath of the Big Bang, the universe was an unimaginably hot, dense, and energetic plasma. It was far too hot for atoms or even stable atomic nuclei to exist. Instead, the universe was a chaotic, rapidly expanding soup of elementary particles, quarks, leptons, like electrons and neutrinos, and photons, particles of light. This initial period, lasting only a tiny fraction of a second, saw the formation of these fundamental particles. As the universe continued to expand, it also cooled. Within the first few microseconds, quarks coalesced to form protons and neutrons, the building blocks of atomic nuclei. Still, the temperature remained incredibly high, preventing these protons and neutrons from binding together into more complex structures. The universe was still a fiery cauldron, with particles constantly colliding and breaking apart. However, a crucial window opened for nuclear synthesis during the first few minutes after the Big Bang. As the universe continued its rapid expansion, the temperature and density dropped to a critical point where a process known as Big Bang nucleosynthesis could occur. This was the cosmic forge where the very first atomic nuclei were created. Protons and neutrons began to fuse together. The vast majority of these fusion reactions resulted in the formation of hydrogen nuclei. A hydrogen nucleus is the simplest atomic nucleus, consisting of just a single proton. This makes hydrogen the lightest and most abundant element in the entire universe. Roughly 75% of the ordinary matter in the cosmos is hydrogen. Alongside hydrogen, a smaller but still significant amount of helium nuclei were formed, each consisting of 2 protons and 2 neutrons. Trace amounts of lithium, an element with 3 protons, were also produced. It is absolutely crucial to note that no heavier elements, such as carbon, nitrogen, or oxygen, were formed during Big Bang nucleosynthesis. The conditions, specifically the temperatures and densities, were simply not conducive to the more complex nuclear reactions required to build elements beyond lithium. The window for this primordial nucleosynthesis was also incredibly brief, lasting only about 3 to 20 minutes. After this short period, the universe had expanded and cooled too much for these nuclear reactions to continue. The energy was too low, and the particles were too spread out for significant further fusion to occur. So, for hundreds of millions of years following the Big Bang, the universe remained a vast, diffuse cloud composed almost entirely of hydrogen and helium, with only a minute sprinkling of lithium. This era is sometimes referred to as the Dark Ages, because there were no stars to illuminate the cosmos. The universe was filled with neutral hydrogen and helium atoms, slowly gravitating together in the darkness. These ancient hydrogen atoms were the raw, fundamental material, present from the very beginning. They were essentially waiting, floating through the cold, expanding universe, ready to eventually combine with another element to form more complex molecules, including water. This waiting period was immense, stretching over hundreds of millions of years, during which gravity slowly began to sculpt the cosmic landscape, pulling together these diffuse clouds into denser clumps. These clumps would eventually give birth to the first stars, the hydrogen we find in every water molecule on Earth, in every comet, and in every molecular cloud across the universe, is a direct legacy of this Big Bang nucleosynthesis. It is the most ancient ingredient of water, a timeless relic from the very beginning of existence. Its omnipresence is a testament to the fundamental processes that shaped the earliest moments of our cosmos. Without this initial, abundant creation of hydrogen, the universe's chemical evolution, and ultimately the formation of water and life, would have been impossible. Hydrogen truly is the primordial building block, the universal solvent that sets the stage for all subsequent cosmic chemistry. Having established hydrogen's ancient birth from the Big Bang, our cosmic narrative now turns to the origin of water's other indispensable partner, oxygen. Unlike hydrogen, oxygen is not a primordial element. Its story is one of stellar fires and cosmic alchemy, forged in the intense environments of massive stars. This fundamental difference in origin is key to understanding when and where water could first appear in the universe. For hundreds of millions of years after the Big Bang, the universe was primarily composed of hydrogen and helium. There were no heavier elements like oxygen. It was a chemically simple cosmos. However, gravity was relentlessly at work, slowly pulling together the densest clumps of this primordial gas. As these colossal clouds of hydrogen and helium collapsed under their own immense gravity, their cores became incredibly hot and dense. Eventually, the pressure and temperature at the centers of these collapsing clouds reached millions of degrees, igniting nuclear fusion. This was the birth of the first stars. These first stars, often referred to as population 3 stars, were very different from our Sun. They were enormous, potentially hundreds of times the mass of our Sun, and burned through their nuclear fuel at an astonishing rate. Their lives were short, but incredibly impactful. In their scorching cores, hydrogen atoms were fused together to create helium, releasing vast amounts of energy that made these stars shine brightly. But to create oxygen, the story needs even more extreme conditions and much more massive stars. As a massive star exhausts the hydrogen fuel in its core, gravity causes the core to contract and heat up further. This increased temperature and pressure allow helium atoms to fuse together, primarily forming carbon. This process marks a significant step in the star's evolution as it begins to build heavier elements. For oxygen to form, the star must be truly colossal, at least 8 to 10 times the mass of our Sun. These giant stars continue their nuclear fusion journey beyond carbon. Once the helium in the core is depleted, the core contracts again, raising temperatures to hundreds of millions of degrees. At these extreme temperatures, carbon nuclei can fuse together to create even heavier elements like neon, sodium, magnesium, and most crucially for our story, oxygen. This process continues in successive layers within the star's core, much like an enormous cosmic onion. In the innermost regions, heavier elements are created, while lighter elements are still fusing in the outer layers. Eventually, these massive stars can fuse elements all the way up to iron. The creation of oxygen, therefore, is an ongoing process within the lives of these massive, short-lived stars. They are the universe's natural alchemists, transforming the simple hydrogen and helium born in the Big Bang into the diverse array of heavier elements that make up planets and life. However, for this newly forged oxygen to become available for water formation, it must be released from the star. This happens in the most spectacular way imaginable, through a supernova explosion. When a star significantly more massive than the Sun runs out of nuclear fuel capable of sustaining fusion in its core, the outward pressure from fusion can no longer counteract the immense inward pull of gravity. The core collapses rapidly and catastrophically, triggering an enormous explosion that briefly outshines entire galaxies. This is a supernova. In the cataclysmic blast of a supernova, the tremendous shockwaves and extreme conditions not only scatter the heavy elements previously forged in the star's core into interstellar space, but they can also trigger a final burst of nucleosynthesis, creating even more heavy elements, including additional oxygen. This violent ejection of matter enriches the surrounding interstellar medium, the vast space between stars, with a fresh supply of oxygen, along with other essential elements like carbon, nitrogen, silicon, and iron. This process of stellar birth, life, and explosive death is absolutely fundamental to the creation of oxygen and, by extension, water. Without these cycles, the universe would remain chemically primitive, a barren expanse of hydrogen and helium. The successive generations of stars gradually pollute the cosmos with these heavier elements, which astronomers collectively refer to as metals, even though this includes elements like oxygen and carbon, which are not metals in our everyday understanding. This enrichment is a prerequisite for the formation of rocky planets, complex molecules, and ultimately, life itself. So, the oxygen in every water molecule we encounter is a direct descendant of a long-dead massive star, ejected into space in a brilliant supernova. This means that water, as a molecule, could only begin to form after the first generation of massive stars had lived and died, enriching the universe with the necessary oxygen. This temporal separation between the creation of hydrogen and oxygen is a key piece of the puzzle, guiding us to the next stage of water's journey. its actual assembly in the cold, dark recesses of interstellar space. With hydrogen established as a legacy of the Big Bang and oxygen as a fiery gift from the hearts of massive, long-dead stars, the ingredients for water are finally present in the universe. But how do these disparate atoms, formed at different times and in vastly different cosmic environments, actually come together to form the familiar H2O molecule? The answer lies in the universe's interstellar ice factories, the vast, cold, dark molecular clouds that permeate galaxies. These are not merely empty spaces. They are dynamic chemical reactors, the true birthplaces of water molecules. After massive stars explode as supernovae, they scatter the oxygen they forged into the interstellar medium. This newly minted oxygen then mixes with the ancient hydrogen that has been present since the Big Bang. Over immense stretches of cosmic time, gravity continues to act on these diffuse clouds of gas and dust, pulling them together into denser, colder regions. These are the giant molecular clouds, colossal structures that can span hundreds of light years and contain enough material to form millions of stars. They are often visible as dark, opaque patches against the starry background, because their dense dust blocks out the light from more distant stars. It is within these frigid, dense molecular clouds that the conditions become just right for atoms to meet, react, and bond. The temperatures are incredibly low, typically hovering around 10 to 20 Kelvin above absolute zero, which is approximately negative 442 to negative 423 degrees Fahrenheit. At such extreme cold, atoms and molecules move very slowly. This reduced kinetic energy means that when atoms collide, they are more likely to stick together rather than simply bouncing off each other, increasing the probability of forming stable chemical bonds. Moreover, the density of these clouds, while still far less dense than Earth's atmosphere, is significantly higher than the average interstellar space. This higher density increases the frequency of collisions between atoms, facilitating the chemical reactions necessary for molecule formation. The primary mechanism for water formation in these cold molecular clouds involves reactions occurring on the surfaces of tiny dust grains. These microscopic dust particles, which are also products of dying stars, act as cosmic catalysts. Imagine these dust grains as tiny platforms floating through the cloud. When a hydrogen atom drifts by, it can adhere to the surface of a dust grain. Soon after, another hydrogen atom might land nearby, followed by an oxygen atom. The dust grain provides a stable surface where these atoms can migrate, encounter each other, and overcome the small energy barrier required to form chemical bonds, often involving the release of a small amount of energy, which can be dissipated into the dust grain, thus stabilizing the newly formed molecule. One common pathway involves the formation of a hydroxyl radical, OH. An oxygen atom can react with a hydrogen atom on a dust grain to form OH. This hydroxyl radical can then readily pick up a second hydrogen atom to complete the water molecule, H2O. Another pathway involves atomic hydrogen reacting with molecular oxygen, O2. Though molecular oxygen is generally less abundant than atomic oxygen in many regions of these clouds. The key is the efficient binding of hydrogen and oxygen atoms together in a relatively protected, cold environment. Once water molecules form, they immediately freeze onto the cold surfaces of these dust grains, forming icy mantles. These icy layers accumulate over time, creating layers of water ice along with other simple, volatile molecules like carbon monoxide, carbon dioxide, ammonia, and methane. These ice-coated dust grains are critical because they represent the primary reservoir of water in the early universe, before the formation of stars and planets. They are essentially cosmic snowflakes, carrying the promise of liquid water to future planetary systems. The significance of this process cannot be overstated. The very first water molecules in the universe did not appear in liquid form. They were created as solid ice in the frigid, dark recesses of interstellar space, far from any star. This initial formation of water ice is not a minor detail. It is the fundamental mechanism by which water became incorporated into the raw material from which stars and planets would eventually form. Without these icy dust grains acting as chemical assembly lines, the seeds of future oceans would never have been sown into the nascent solar systems. Thus, while the elements of water have ancient and stellar origins, the water molecule itself first came into being relatively early in cosmic history. Once enough massive stars had lived and died to enrich the interstellar medium with oxygen. Its presence in these vast, cold molecular clouds signals a universe becoming chemically complex, a universe capable of assembling the intricate molecules that would eventually lead to planets, and perhaps to life. These interstellar ice factories are where water's long cosmic journey truly takes shape, preparing it for its next great adventure, incorporation into new solar systems. Having witnessed water's assembly as ice on dust grains within frigid molecular clouds, our cosmic narrative now transitions to the next crucial phase: water's journey into forming solar systems and its storage within the swirling material of protoplanetary disks. These disks are the direct predecessors of planetary systems like our own, and they represent the vital intermediary step between diffuse interstellar ice and the potential for liquid water on planets. When a dense core within a giant molecular cloud begins to collapse under its own gravity, it eventually forms a protostar, a nascent star that has not yet begun nuclear fusion in its core. As the protostar grows, the surrounding gas and dust, unable to fall directly into the central object, flattens out into a rotating pancake-like structure. This is known as a protoplanetary disk, also sometimes called a circumstellar disk. These disks are essentially the construction sites for planets, asteroids, and comets, and they are absolutely teeming with the ice-coated dust grains that carry the universe's water. The conditions within a protoplanetary disk are not uniform, and this heterogeneity is crucial for the distribution of water. Close to the protostar, temperatures are extremely high due to the intense radiation and heat emanating from the forming star. In this innermost region of the disk, the water ice that coats the dust grains, along with other volatile ices, sublimates directly into a gaseous state. This creates a region of water vapor in the inner part of the disk. Any rocky planetesimals forming in this hot zone would initially accrete from largely dry, rocky material, having lost their icy mantles. However, farther away from the protostar, at greater distances, temperatures remain low enough for water to persist as solid ice. This critical boundary is known as the snow line or ice line. Beyond the snow line, temperatures typically drop below approximately 170 Kelvin, or about negative 153 degrees Fahrenheit, allowing water to remain frozen. This snowline is not a static boundary. It can move inwards or outwards depending on the luminosity of the central star and the dynamics of the disk. The snowline is a profoundly important feature in planetary formation because it dictates where icy bodies can form, and it profoundly influences the composition of the planets that eventually emerge from the disk. In the inner region, inside the snowline, planetesimals and subsequently rocky planets like Earth, Mars, and Venus predominantly form from silicate rock and metal, with very little native water. Conversely, the region beyond the snowline is where icy bodies can readily accumulate. The abundance of solid water ice, along with other frozen volatiles like carbon dioxide, methane, and ammonia, provides a vast amount of solid material for planetesimals to accrete. These icy planetesimals can grow rapidly, accumulating more mass much faster than their rocky counterparts in the inner disk. When these icy cores reach a critical mass, they become massive enough to gravitationally capture large envelopes of hydrogen and helium gas from the surrounding disk, thus forming gas giant planets like Jupiter and Saturn. The composition of these gas giants, particularly their deep atmospheres and potentially icy cores, contains immense reservoirs of water, much of it originating from the primordial ice in the disk. The water incorporated into these protoplanetary disks, whether in its gaseous state near the star or as solid ice beyond the snowline, is a direct inheritance from the molecular clouds where it first formed. It represents a continuous thread in water's cosmic journey, demonstrating how water is not just a terrestrial phenomenon, but an intrinsic and abundant component of the entire star and planet-forming process. The existence of these vast reservoirs of water within protoplanetary disks means that the potential for water-rich planets is inherent in the very mechanism of planet formation itself. Observations of distant stellar nurseries and protoplanetary disks, utilizing advanced telescopes like the Atacama Large Millimeter Submillimeter Array, or ALMA, have provided direct evidence for this scenario. These observations can map the distribution of water vapor and ice in young protoplanetary disks, confirming the presence of significant amounts of water, and often revealing the distinct boundary of the snowline. These astronomical insights allow us to essentially watch the cosmic water cycle in action, from its diffuse origins in molecular clouds to its concentration within disks where planets are beginning to assemble. The sheer volume of water estimated to be present in some of these protoplanetary disks is astonishing, often enough to fill Earth's oceans many, many times over. This speaks to the efficiency of cosmic chemistry and gravitational processes in concentrating this vital molecule. It reinforces the idea that water is not a rare anomaly in the universe, but rather a common ingredient in the recipe for forming stars and their attendant planetary systems. This understanding is foundational as we move to the next stage of water's story, its delivery to nascent planets. As planets begin to coalesce within the protoplanetary disk, a critical question emerges for worlds forming in the inner, hotter regions. How do they acquire water if their immediate surroundings are too warm for ice? This brings us to the crucial role of comets and asteroids, the icy messengers that delivered vast quantities of water to nascent planets, fundamentally shaping their potential for habitability. These relatively small celestial bodies are, in essence, ancient time capsules, preserving primordial water and other volatile compounds from the earliest days of our solar system. Let us first distinguish between these two important types of icy couriers. Asteroids are generally rocky or metallic bodies, primarily found in the asteroid belt between Mars and Jupiter. They are considered remnants of the early solar system that never quite managed to coalesce into full-fledged planets. While many asteroids are relatively dry, a significant subset, particularly those located in the outer parts of the asteroid belt, known as carbonaceous chondrites, are rich in water. This water is often trapped within their mineral structures as hydrated minerals or as small pockets of ice. These water-rich asteroids are thought to have formed beyond the initial solar system snowline, where ice was plentiful, and were later scattered inwards by the gravitational influence of the gas giant planets. Comets, on the other hand, are often vividly described as dirty snowballs. They are predominantly composed of ice, a mixture of water ice, frozen carbon dioxide, carbon monoxide, methane, and ammonia, interspersed with dust and rocky material. Comets originate much further out in the solar system, primarily from two vast, distant reservoirs. The Kuiper Belt, a disc-shaped region beyond Neptune, populated by icy bodies, and the even more remote Oort cloud, a spherical shell of icy objects extending almost a light year from the Sun. When these comets are gravitationally perturbed from their distant, stable orbits, often by the influence of gas giant planets or passing stars, they can be sent hurtling inwards towards the Sun and the inner solar system, where they become visible as their ices sublimate, forming characteristic glowing comas and tails. During the early, chaotic phases of solar system formation, and particularly during a period known as the Late Heavy Bombardment, roughly 4 billion years ago, both asteroids and comets would have rained down on the newly forming inner planets. Each impact would have represented a delivery of material, including a potentially significant amount of water. The central challenge for planetary scientists has been to determine the relative contribution of comets versus asteroids to Earth's total water budget, and potentially to other inner solar system bodies. The key to distinguishing between these potential sources lies in the isotopic signature of water, specifically the ratio of deuterium, a heavier isotope of hydrogen with an extra neutron, to normal hydrogen. This DH ratio acts as a unique chemical fingerprint, varying depending on the conditions under which the water formed and the specific region of the solar system it originated from. By comparing the DH ratio of Earth's ocean water to the DH ratios measured in various types of comets and asteroids, scientists can gain crucial insights into the most likely sources of our planet's water. Early measurements of comets, especially those from the Jupiter family, originating in the Kuiper Belt, often revealed DH ratios that were significantly higher, 2 to 3 times higher, than that of Earth's oceans. This led many scientists to initially conclude that these types of comets could not have been the primary source of Earth's water, or at least not the sole source. However, more recent measurements of comets from the Oort cloud, such as Comet 67P Churyumov-Gerasimenko, which was extensively studied by the European Space Agency's Rosetta mission, have shown DH ratios that are closer to Earth's water, though still somewhat elevated. This suggests that the cometary population is diverse, and some types of comets might have contributed more than others. Conversely, a particular class of meteorites, known as carbonaceous chondrites, which are believed to originate from asteroids in the outer asteroid belt, have consistently shown DH ratios that are strikingly similar to Earth's ocean water. These meteorites also contain a significant amount of water, often several percent by mass, locked within their mineral structures, or as hydrated minerals. This strong isotopic match has significantly bolstered the argument that carbonaceous chondrites, or the parent asteroids from which they broke off, were a major, if not the dominant, source of water for Earth. These asteroids formed in a region of the protoplanetary disk, just beyond the snow line, where water ice was abundant, but were also close enough to the inner solar system to be gravitationally scattered inwards through dynamic processes involving the gas giants. It is important to emphasize that this water delivery was not a gentle, single event. It was a prolonged and often violent bombardment lasting for hundreds of millions of years during the early history of the solar system. Even if some water was lost to space due to energetic impacts or atmospheric escape during these collisions, the sheer volume of incoming water-rich material over time would have ensured a net accumulation. Furthermore, some models suggest that water could have been incorporated into Earth's mantle during its formation and later outgassed through volcanic activity, providing an additional, though likely secondary, contribution to surface water. The implications of this icy messenger delivery system extend far beyond Earth. If the mechanism of water delivery via comets and asteroids is a common feature of planet formation in other star systems, it significantly increases the likelihood of finding water-rich exoplanets. The material ejected from the outer, ice-rich regions of a protoplanetary disk can be gravitationally scattered inwards to the habitable zones around other stars, providing the essential ingredient for life. This potentially universal mechanism strengthens the case for widespread watery worlds across the cosmos. Ultimately, the water that now graces our planet, making it the vibrant, living world we inhabit, is a cosmic inheritance. It is a legacy of the icy materials that formed far from the sun in the protoplanetary disk, subsequently delivered through billions of years of cosmic collisions and gravitational interactions. These seemingly small, humble objects, the comets and asteroids, played an absolutely monumental role in transforming inner, rocky worlds from dry, desolate spheres into vibrant, potentially life-sustaining havens. They are the ancient couriers of cosmic water, bridging the vast distances of the solar system and delivering the most precious commodity for life. With the stage now set for water's delivery to nascent planets, our focus narrows to one of the most profound and actively debated questions in planetary science. How did our own Earth acquire its magnificent, life-sustaining oceans? The genesis of Earth's oceans is not merely a local curiosity. It is a critical case study in understanding the cosmic journey of water, representing the culmination of billions of years of formation and transport, resulting in the liquid medium essential for life as we know it. There are several compelling theories, each supported by various lines of evidence, that attempt to unravel the complex history of our planet's hydrosphere. Earth formed approximately 4.54 billion years ago through the process of accretion, where smaller planetesimals gradually collided and merged in the inner solar system. As we have discussed, the region where Earth initially formed was likely too hot for water ice to persist. This initial condition strongly suggests that the bulk of Earth's water must have been delivered from external sources, originating from the colder, outer reaches of the protoplanetary disk. The two primary external candidates for this delivery, as established, are carbonaceous chondrite asteroids and comets, each possessing distinct isotopic fingerprints and orbital dynamics. One of the most widely accepted theories, currently favored by much of the scientific community, posits that the majority of Earth's water was delivered by carbonaceous chondrite asteroids. These meteorites, thought to originate from the outer asteroid belt, formed beyond the solar system's snowline, allowing them to incorporate significant amounts of water, both as ice and trapped within their mineral structures as hydrated silicates. When these water-rich asteroids bombarded the early Earth, they contributed their water payload. The key piece of evidence supporting this theory is the remarkable similarity between the deuterium to hydrogen DH ratio found in Earth's ocean water and that measured in many carbonaceous chondrite meteorites. This isotopic match serves as a powerful geochemical fingerprint, strongly suggesting a common origin. The bombardment by these asteroids would have been a prolonged process, particularly intense during the tumultuous period known as the Late Heavy Bombardment, gradually accumulating the water that would form our planet's early oceans. A second prominent theory, which has seen fluctuating levels of scientific support over time, suggests that comets played a more substantial role in Earth's water delivery. Comets, being essentially giant dirty snowballs originating from the distant Kuiper Belt and Oort cloud, are rich in water ice. A continuous, long-term bombardment of comets could certainly have delivered a significant amount of water. However, a key challenge for this theory has been the DH ratio. Many comets, particularly those from the Jupiter family, exhibit a DH ratio that is significantly higher than that of Earth's oceans, making them unlikely candidates for the primary source. Nevertheless, the diversity of cometary populations means that some types, perhaps those yet to be fully sampled, might possess a DH ratio closer to Earth's. It is also plausible that a mix of sources contributed, with comets playing a smaller but still meaningful role alongside asteroids. Ongoing space missions to study various comets are continuously refining our understanding. Beyond external delivery, there is also the concept of endogenous water, or water that was incorporated into Earth's interior during its formation from the initial building blocks. While Earth initially accreted from largely dry material in its immediate formation zone, some models suggest that small amounts of water could have been chemically bound within the rocky components that formed the planet. As the Earth differentiated into its core, mantle, and crust, and as geological processes like volcanism began, this internally trapped water could have been gradually outgassed from the planet's interior, contributing to the formation of the atmosphere and subsequently the oceans. This is not typically considered the primary source, but rather a potentially complementary one, adding to the externally delivered water over geological timescales. Regardless of the exact proportions contributed by asteroids, comets, or internal processes, the actual formation of liquid oceans on Earth would have been a multifaceted and dynamic process. After its initial violent accretion phase, the early Earth would have been an incredibly hot, molten body, often referred to as a magma ocean. Any delivered water would have rapidly vaporized, forming a dense, steamy, supercritical atmosphere. As the planet gradually cooled over millions of years, this atmospheric water vapor would eventually condense, forming vast cloud systems and subsequently leading to torrential, planet-wide rain. This continuous rainfall, potentially lasting for millions of years, would have filled the planet's basins, eventually forming the first primitive oceans. This cooling phase was absolutely critical, allowing the planet to transition from a magma ocean to a water ocean world. The early Earth's evolving atmosphere also played a crucial role in retaining this newly acquired water. A sufficiently dense atmosphere, coupled with Earth's gravitational pull, would prevent the water vapor from simply escaping into space. Over time, as the planet continued to cool and stabilize, the hydrological cycle, driven by solar energy, would have become firmly established, leading to the continuous circulation of water between oceans, atmosphere, and land, shaping the planet's climate and geology. Understanding the timing of ocean formation is equally critical for the origin of life. Liquid water is universally considered a prerequisite for life as we know it. Geological evidence suggests that liquid water was present on Earth's surface surprisingly early in its history, perhaps as early as 4.4 billion years ago, not long after the planet itself formed. This early appearance of oceans provides a crucial window for the emergence of life, which geological evidence suggests may have begun as far back as 3.8 billion years ago, establishing the profound link between water and life. The various theories surrounding Earth's ocean formation are not necessarily mutually exclusive. It is highly probable that a combination of these mechanisms was at play, with certain sources dominating at different stages of Earth's tumultuous early history. The most current understanding leans towards carbonaceous chondrite asteroids as the primary source, possibly supplemented by a smaller contribution from specific types of comets, and perhaps some outgassing from the planet's interior. The ongoing research in geochemistry, planetary dynamics, and astronomical observations continues to refine these complex models, bringing us ever closer to a complete and nuanced understanding of how our beautiful blue planet became a water world, a veritable oasis in the cosmos. While Earth proudly stands as a vibrant testament to the power of liquid water and its ability to nurture life, the cosmic journey of water extends far beyond our blue marble. The widespread presence of water in various forms, ice, vapor, and even vast subsurface liquid oceans, across our solar system and increasingly in distant exoplanetary systems, is a powerful indicator of its cosmic abundance and its fundamental role in planetary evolution. Discovering water beyond Earth is not merely about finding more H2O. It is about uncovering potential habitats, unraveling the intricate histories of other worlds, and ultimately, profoundly influencing our search for extraterrestrial life. Within the confines of our own solar system, water is surprisingly ubiquitous, although often in states very different from Earth's expansive liquid oceans. Even Mercury, the closest planet to the Sun and a world of extreme heat, harbors water. Radar observations have revealed strong evidence of water ice hidden within the permanently shadowed craters at its poles. In these deep depressions, sunlight never reaches the surface, allowing temperatures to remain frigid enough to preserve ice, likely delivered by comet or asteroid impacts over billions of years. Venus, often called Earth's scorching twin, possesses a super-dense atmosphere composed primarily of carbon dioxide, with surface temperatures hot enough to melt lead. While it is believed to have once harbored surface liquid water billions of years ago, a runaway greenhouse effect caused this water to boil away and largely escape into space. However, trace amounts of water vapor can still be found in its upper atmosphere, a lingering ghost of its watery past, indicating that water was once a more significant component of this planet. Mars, the enigmatic red planet, is perhaps the most captivating world in our solar system for the search for past and present water, and by extension, life. Geological features such as ancient riverbeds, sprawling deltas, and mineral deposits that definitively form only in the persistent presence of liquid water provide compelling evidence that Mars once hosted significant amounts of surface liquid water billions of years ago. Today, most of Mars's water is locked up as solid ice in its polar caps, beneath the surface in vast glaciers, and likely as pervasive permafrost. Recent discoveries by orbiters and rovers have even found tantalizing evidence of briny liquid water occasionally flowing on the surface during warmer seasons, though this phenomenon is still under active investigation. The primary focus of current and future Mars missions continues to be the hunt for subsurface liquid water reservoirs, where it might be protected from the harsh surface radiation and extreme cold. Moving to the outer solar system, the gas giants, Jupiter and Saturn, are enormous reservoirs of hydrogen and helium, but they also contain significant amounts of water. In their deep, cold atmospheres, water exists as vapor and ice crystals, forming clouds that contribute to their complex and dynamic weather patterns, as seen in Jupiter's famous Great Red Spot or Saturn's hexagonal polar storm. However, the most thrilling discoveries of water in the outer solar system come from the icy moons of these gas giants. Jupiter's moon Europa is widely considered one of the prime candidates for hosting extraterrestrial life. Beneath its dramatically cracked and relatively young icy shell, which can be tens of kilometers thick, compelling evidence strongly suggests the presence of a vast saltwater ocean, potentially larger than all of Earth's oceans combined. This subsurface ocean is believed to be kept liquid by tidal heating, generated by Jupiter's immense gravitational forces. Missions like the upcoming Europa Clipper are specifically designed to investigate this ocean further, searching for signs of potential habitability and even direct evidence of life. Similarly, Jupiter's largest moon, Ganymede, also shows strong indications of a subsurface ocean, possibly sandwiched between multiple layers of ice. Callisto, another of Jupiter's large Galilean moons, is also thought to harbor a deep subsurface ocean. Saturn's moon Enceladus is another incredibly compelling ocean world. Geysers erupt dramatically from its south pole, spewing plumes of water vapor and ice particles hundreds of kilometers into space. These plumes originate from a subsurface liquid ocean that is in contact with a rocky core, making it a highly dynamic and potentially chemically active environment. The Cassini mission famously flew through these plumes, detecting not only water, but also complex organic molecules and various salts, all crucial ingredients for life. Titan, Saturn's largest moon, which already boasts a thick nitrogen-rich atmosphere and surface lakes of liquid methane and ethane, also contains a vast subsurface ocean of liquid water and ammonia, kept warm by a combination of radioactivity and tidal heating. Even farther out, Uranus and Neptune, often termed ice giants, are thought to have deep interiors composed of a mixture of water, ammonia, and methane ices and liquids under extreme pressures and temperatures. These planets are, in a fundamental sense, giant water worlds, albeit under conditions far removed from the surface conditions of Earth. Beyond our solar system, the discovery of water on exoplanets and within exoplanetary systems is rapidly expanding our cosmic perspective. Using powerful telescopes like the Hubble Space Telescope and, more recently, the revolutionary James Webb Space Telescope, astronomers have detected distinct spectral signatures of water vapor in the atmospheres of numerous exoplanets, including scorching hot Jupiters and cooler Neptune-sized worlds. The James Webb Space Telescope, with its unprecedented infrared capabilities, is particularly adept at detecting water's subtle spectral signatures in the atmospheres of distant worlds, even those in the habitable zones of their stars. The confirmed presence of water vapor in an exoplanet's atmosphere is a crucial, though not singular, step towards identifying potentially habitable worlds, especially those orbiting within their star's habitable zone, where liquid water could theoretically exist on the surface. Furthermore, continued observations of protoplanetary disks around young stars reveal substantial amounts of water ice and vapor, confirming that the processes of water formation and delivery are universal and inherent to star and planet formation. This widespread cosmic distribution of water, from the frigid poles of Mercury to the deep, hidden oceans of exomoons and the vast atmospheres of distant exoplanets, reinforces the idea that water is not a rare anomaly, but a common and fundamental component of the universe. Each new discovery of water beyond Earth brings us closer to understanding the conditions under which life can arise, strengthening the profound connection between water and the ultimate question of whether we are truly alone in the cosmos. The grand cosmic journey of water culminates in its most profound and exhilarating implication: its crucial, undeniable link to life's potential. This connection gives rise to what we call the astrobiological imperative, the driving scientific quest to understand the origin, evolution, distribution, and future of life in the universe, with water as its central focus. Water is not merely a benign backdrop for life. It is an active, indispensable participant in the complex chemical reactions that underpin all known biological processes, making its widespread presence across the cosmos a powerful beacon of hope in the search for extraterrestrial life. Astrobiology is a multidisciplinary field, drawing from astronomy, biology, chemistry, geology, and physics, all converging on the fundamental questions surrounding life beyond Earth. At the very heart of astrobiology lies an intense preoccupation with water, because, on our home planet, every single known form of life, from the simplest single-celled organisms to the most complex multicellular beings, absolutely relies on liquid water for its existence and survival. This profound dependency is not a mere coincidence. It stems directly from water's extraordinary and unique physical and chemical properties. Firstly, water is an exceptional solvent. Its polar molecular structure, with a slight positive charge on the hydrogen atoms and a slight negative charge on the oxygen atom, allows it to dissolve an incredibly wide range of substances, both ionic and polar. This universal solvent capability is vital for life because it facilitates the transport of essential nutrients into cells and the efficient removal of waste products. Within the intricate biochemical factories of living cells, water acts as the indispensable medium in which countless metabolic reactions occur, bringing reactants into close proximity and allowing life's complex chemistry to proceed with remarkable efficiency. Without this solvent capability, biological molecules would struggle to interact effectively, severely hampering the processes necessary for metabolism, growth, and replication. Secondly, water possesses a remarkably high specific heat capacity. This means it can absorb and release a large amount of heat energy with only a relatively small change in its own temperature. This property is absolutely vital for temperature regulation, operating on both a planetary scale and within individual organisms. Earth's vast oceans act as enormous heat sinks, moderating our planet's climate and preventing the extreme sudden temperature swings that would be profoundly detrimental to life. Similarly, within our own bodies, water helps to maintain a stable internal temperature, protecting delicate cellular machinery from overheating or freezing, ensuring optimal enzyme function. Thirdly, one of water's most peculiar and life-enabling properties is that it is less dense as a solid, ice, than as a liquid. This characteristic is almost unique among common substances. If ice were denser than liquid water, as most solids are, lakes and oceans would freeze solid from the bottom up in cold climates, making it virtually impossible for aquatic life to survive the winter. Because ice floats, it forms an insulating layer on the surface of bodies of water, protecting the liquid water below from further freezing and allowing life to persist in frigid conditions. This property is particularly relevant for the subsurface oceans found on icy moons like Europa and Enceladus, where a thick ice shell provides protection from the harsh radiation and vacuum of space, while the liquid water underneath remains stable. Fourthly, water is not just a passive medium. It is a reactive molecule, participating directly in numerous fundamental biochemical reactions. For instance, it is a reactant in hydrolysis, a process used to break down complex molecules into simpler ones, and it is a product of dehydration synthesis, where smaller molecules are joined together to form larger ones. Water is also directly involved as a reactant or product in photosynthesis and cellular respiration, the fundamental processes that drive most ecosystems on Earth. Given these indispensable properties, scientists have long focused on the concept of the habitable zone, or Goldilocks zone, around a star. This zone defines the range of orbital distances where conditions are theoretically just right for liquid water to exist stably on a planet's surface, not too hot for water to evaporate into space, and not too cold for it to freeze solid. However, the groundbreaking discoveries of vast subsurface oceans on icy moons like Europa and Enceladus have broadened this definition considerably. These moons exist far outside the traditional habitable zone of our Sun, yet they harbor substantial reservoirs of liquid water, kept warm by internal processes such as tidal heating and radioactive decay. This has led to the exciting concept of ocean worlds, where life might thrive beneath protective icy shells, largely independent of the heat from their central star. The astrobiological imperative, therefore, drives much of our current space exploration. Missions to Mars continue to search for signs of past or present liquid water, and, by extension, ancient or extant microbial life, particularly in subsurface environments where conditions might be more favorable. Missions like the upcoming Europa Clipper are specifically designed to investigate Europa's subsurface ocean, with sophisticated instruments aimed at detecting organic molecules, energy sources, and other biosignatures that could indicate the presence of life. The data collected from these missions directly feeds into our understanding of life's potential beyond Earth and helps refine our models of habitability. The widespread discovery of water, often in its icy form, across the cosmos, from the diffuse molecular clouds where stars are born to the protoplanetary disks where planets form, from the frigid poles of Mercury to the deep interiors of ice giants and the vast atmospheres of distant exoplanets, is immensely encouraging for astrobiology. It strongly suggests that the fundamental ingredient for life, liquid water, is not a rare cosmic anomaly. While the precise conditions required for stable, long-lived liquid water on a planetary surface might be more stringent, the sheer abundance of H2O in the universe means that the basic building blocks are universally available. However, it is crucial to remember that while water is an absolute necessity for life as we currently understand it, its presence alone is not sufficient. A truly habitable world also requires a stable energy source, a supply of basic organic molecules, the carbon-based compounds that form the backbone of life, and a long enough period of environmental stability for life to emerge, evolve, and potentially thrive. But without water, the conversation about habitability often ends before it even begins. The cosmic journey of water is thus intrinsically linked to the profound quest for life, serving as the primary guide in our ongoing search for other potentially living worlds in the vast, star-studded cosmos. Every detection of water, whether vapor, ice, or liquid, nudges us closer to answering one of humanity's most profound questions. Are we alone in this magnificent universe? Our incredible journey, tracing the origin of water from the very first moments of the universe to its profound link with life's potential, now brings us to consider the ultimate future of water in our ever-expanding and evolving cosmos. The universe is not a static entity. It is a dynamic realm where stars are born and die, galaxies merge, and planets undergo transformations over immense timescales. What, then, is the ultimate destiny of water, this molecule so fundamental to life in such a perpetually changing environment? Let us first peer into the long-term future of water within our own solar system, specifically focusing on Earth. The long-term prognosis for liquid surface water on our planet is inextricably tied to the inexorable evolution of our Sun. Our Sun is currently a stable, main-sequence star, steadily fusing hydrogen into helium in its core. However, in approximately 1 billion to 1.5 billion years from now, as the Sun continues to age and consume its core hydrogen fuel, its luminosity will gradually increase. This means it will get hotter and brighter. As the Sun's energy output intensifies, Earth will experience a slow but relentless warming. This warming will inevitably trigger a runaway greenhouse effect, a catastrophic process similar to what occurred on Venus, but on a much grander, planet-wide scale. As Earth's temperatures rise, more and more water from its vast oceans will evaporate into the atmosphere. Water vapor is a potent greenhouse gas, and this increased atmospheric water will trap even more heat, leading to further evaporation in a devastating feedback loop. Eventually, all of Earth's surface water, every ocean, sea, and lake, will boil away, leaving behind a parched, desolate planet. This vast amount of atmospheric water vapor will then be subjected to intense ultraviolet radiation from the increasingly powerful sun, which will photodissociate, or split, the water molecules into their constituent hydrogen and oxygen atoms. The lighter hydrogen atoms, being less massive, will then readily escape Earth's diminishing gravitational pull and be lost into space, effectively stripping Earth of its water permanently. This process of photodissociation and atmospheric escape will ensure that Earth becomes an utterly dry world, utterly incapable of supporting life as we know it, long before the sun itself reaches the end of its stellar life. Looking even further into the deep future, in approximately 5 billion years, the sun will exhaust the last of the hydrogen fuel in its core and begin its dramatic evolution into a red giant star. It will expand enormously, engulfing the innermost planets, Mercury and Venus, and quite possibly Earth itself. Even if Earth manages to avoid being fully consumed by the expanding sun, it will be roasted to an incandescent cinder, and any remaining trace amounts of water, deep underground or chemically bound in minerals, will be vaporized and forever lost. The outer gas giants and their icy moons, however, might experience a temporary and paradoxical warming. As the sun expands, its habitable zone will shift outwards, potentially creating a brief period where some of the icy moons of Jupiter and Saturn, like Europa or Enceladus, could experience significant surface melting and transient liquid water. However, this phase would be short-lived, as the sun's ultimate demise as a white dwarf star would leave them once again in a frigid, irradiated, and ultimately dying environment. Beyond our solar system, the future of water is intricately tied to the grand, galactic-scale cycle of stellar birth and death. The fundamental elements that compose water, hydrogen, and oxygen are continuously being recycled throughout the universe. Hydrogen, forged in the Big Bang, remains the most abundant element, a limitless reservoir. Oxygen, perpetually created in the cores of massive stars, is continuously produced and dispersed through spectacular supernova explosions. This ongoing cosmic ballet means that new generations of stars and planets will continue to form from gas clouds enriched with both hydrogen and oxygen, ensuring that water will continue to be a fundamental component of newly forming planetary systems throughout the galaxy for billions of years to come. However, the universe itself is in a state of accelerated expansion. Over unimaginably vast timescales, trillions of years into the future, distant galaxies will recede beyond our observable horizon, and the night sky will become increasingly sparse. The overall rate of star formation will also inevitably decline as the available gas and dust are gradually used up. Eventually, all stars will burn out, leaving behind a cold, dark universe dominated by stellar remnants such as white dwarfs, neutron stars, and the ultimate gravitational singularities, black holes. In this far, far future, the ultimate fate of the vast majority of water will largely be as solid ice trapped within the crusts and deep interiors of dead planets and moons, or as extremely diffuse gas and plasma in the cold emptiness of intergalactic space. With no active stars to provide warmth, any remaining surface liquid water will have long since frozen solid. Over incredibly long epochs, even these icy remnants might eventually succumb to gravitational perturbations, being ejected from their defunct star systems to drift as rogue ice fragments in the unimaginably cold and dark intergalactic void. Ultimately, the chemical bonds of the water molecule, H2O, are incredibly robust and stable. While the state, liquid, solid, gas, and location of water will change dramatically and repeatedly over cosmic time, the molecules themselves will persist for an almost incomprehensible duration, unless subjected to truly extreme energetic processes, such as being torn apart near a supermassive black hole, or during certain particle interactions in the very, very distant future. The very water molecules we see today have existed for billions of years, having been part of molecular clouds, comets, ancient oceans, and perhaps even countless living organisms before finding their way into our present environment. This grand cosmic perspective on water's future serves as a poignant reminder of the preciousness and ultimately fleeting nature of liquid water on habitable worlds like Earth. It underscores the profound significance of our planet's vibrant blue oceans, a temporary but magnificent culmination of billions of years of cosmic evolution. The water that began as primordial hydrogen and stellar oxygen, traveling through interstellar molecular clouds and delivered by icy messengers, found a brief, glorious home as liquid oceans on Earth, allowing life to emerge, diversify, and flourish in an astonishing array of forms. Thank you for joining us on this incredible deep dive into the cosmic origins and future of water, from the Big Bang to the end of time. If you found this journey as fascinating and thought-provoking as we did, please consider giving this video a like and subscribing to Restly for more explorations into the wonders and mysteries of the universe. Sweet dreams.